Probabilistic method. So the idea of this course is to be basic, to not assume that you know anything except like a little graph theory. So if you already know some probabilistic method, probably the first class or two will be very simple for you. Maybe you don't want to come, and then the third and fourth will be a tiny bit more advanced. So it's really for, if you're students who haven't seen this before, it's really for you. Please make me go slowly. Please ask questions. Podem ser em português, sem problemas. I don't want anyone to be feeling shy about their English, okay? So please ask questions. Okay. So the plan is that I'm just going to do some examples, and we're going to talk through the solutions together. We're going to try and solve them together. I've got a list of like 12. We probably won't get through them. It's not a problem. Okay, we just go at the pace the people are happy with. And maybe you've seen some before, maybe not. We'll see. Okay, so here's the first question. So let G be a graph. As I say, it's not really a question, it's a theorem. Every graph G has a bipartite subgraph H with at least half the edges. So someone tell me how to prove this. I guess so. Who's already seen this theorem before? Sorry, who has not seen this? Please, because I want to know how much you know. Who has not seen it before? Great. Good to know. Okay, so let's try to prove it. Right, you give any graph, you can find a bipartite subgraph half the edges. What's your idea? Maybe someone who's seen it before can say.
You can start with a set of two sets of vertices.
Uh-huh.
And you check if moving the vertex from one side to the other.
Exactly. Okay, proof number one, which is not random, is you just do a sort of greedy improvement process. So you take some partition. Okay, so you're getting all the edges in between the two. And if you find a vertex that has more neighbors inside their part than across, well, if you move the vertex to the other side, you increase the number of edges in the bipartition. And if you just keep doing this, eventually it has to stop because you can't increase the number of edges forever. When you get to that point, then every vertex will have at least as many neighbors across as inside, and therefore you must have at least half the edges inside. Right? We're going to get to this, so keep improving, keep swapping vertices until the degree in B of V is at least the degree in A of V for all V in A, and similarly for B. Right? Okay? And then just add up the degrees and add up the edges. It's okay? This is like the standard proof, if you like. Okay, let's do a different proof. So proof 2 is going to be by double counting. Okay? So I guess everyone's seen examples of double counting. So what am I going to count? I'm going to count pairs. Oops. Pairs A, E, where E, the edge E, goes between A and A complement. Okay, so for every subset of the vertices, and every edge, it's going to be true or not. Go ahead. Claro. Você quer fazer a pergunta em português? Você quer que eu fale em português? Qual você quer? Is there anyone here who doesn't speak Portuguese? Sorry.
Actually, the question is, what means that E?
Ah, obrigado. E of G is the number of edges of the graph G. Right? That's all. Sorry. Yeah, so notation I will use, which is not the same as Alex was using, for example. So V of G is the number of vertices of G, and E of G is the number of edges of G. Okay? Thank you. Please, yeah, anytime I use a piece of notation and don't define it, please remind me. Thank you. It's okay? Okay, so you want half the edges to go across. Okay, so we're going to count these pairs such that the edge goes between A and A complement. How many are there? AE. Okay, so you're double counting. You either count the set first, then the edge, or the edge first, then the set. Okay, let's do the edge first. So for each edge, how many choices of A are there? Well, you have the ones where, so suppose E is UV. You could either put U in A and V in A complement, and then the rest of the vertices, you do whatever you like. Right? So that's 2 to the n minus 2 choices. Or you could put U, V in A and U in A complement, and then do what you like with the rest. That's another 2 to the n minus 2 choices. So in total, there are 2 to the n minus 1 choices. Right? Okay. So that's true for every edge. So it's 2 to the n minus 1 times the number of edges of G. Right? For every edge of G, there are 2 to the n minus 1 choices of A such that edge goes between the two sets. Does it make sense? Okay. That was counting the edge first. Okay, what about counting the set A first? Well, let's call f of A the number of edges between A and A complement. Okay? That's exactly the number of edges in this bipartite graph, right? Okay. So that's the same thing as the sum over sets A of f of A. Right? For each set, you want to count all the edges between. That's what I called f of A. We would like there to be a single choice of A such it's bigger than a half. Okay, so suppose that's not true. Then f of A is always strictly less than E of G over 2. So this sum is strictly less than E of G over 2 for every set A. How many sets A? 2 to the n. But that's a contradiction. 2 to the n minus 1 times E of G is not strictly smaller than 2 to the n minus 1 times E of G. They're the same thing. So that's a contradiction. Okay, let's absorb this proof. Make sure we understand what's going on. Okay. So we counted these pairs AE in two ways. We counted each edge, we knew in exactly 2 to the n minus 1. And for each set, we're in some number. If that's smaller than EG over 2, always, then we get a contradiction. Okay? The fact that the number of pairs is this large implies there must be some A for which f of A is at least E of G over 2. Okay. Now, if there are questions, please ask. Okay. I'm now going to do the same proof again, but in different language. So proof 3, which is just proof 2 in disguise. Say choose A randomly. Okay. So our aim is to find this clever bipartition, A and A complement, so that between the two we have half the edges. Instead of being clever, I'm going to be stupid. Okay? Just going to pick it randomly. Let's see what happens. Well, we're interested in this f of a, right? We would like f of a to be at least half of the edges, right? F of a is this number of edges between A and A complement. Okay, but f of a is some very strange random variable that I'm a bit scared of. One of the main messages of this course is, when you have a random variable that you're scared of, just like in Matthew's talk this morning, something that's easy to calculate is the expectation, the average. Okay, so let me do the calculation, and then we'll talk about what happened. What is the expectation of this random variable f of a? So how am I choosing A? I'm choosing A just uniformly at random over all of the subsets. There's 2 to the end of them, stick them in a bag, pull out 1, that's your A. Okay? All the same probability. What is the expectation of f of A? Expectation has this wonderful property. So, should say expectation is just average, right? I'm just saying the average. Is that it's linear. What does that mean? It means we can write it as follows. It's the sum over all edges in the graph. This is the set of edges of the graph. Okay, of the probability that E goes between A and A complement. Okay. So we'll talk a bit more about this later. This is a magic property of expectation. Okay? Goes. I can't spell. Right? He has one endpoint in A, the other in A complement. Okay? To calculate the average, you just sum over all edges that can contribute the probability it contributes. Now, what is this probability? Okay, you've got this edge, UV, calling E, and you're picking a random set A. So how can this edge have one endpoint in A and one in A complement? Well, when we choose A randomly, meaning uniformly at random, that's the same thing as for each vertex tossing a fair coin independently to decide if it goes in A or A complement. Every vertex is in A with probability of half, and A complement probability of half, and they don't affect each other. Right. So exactly 1/4 of the sets A have this property, exactly 1/2 of the sets have this property, right? This is probably half each, this is probably half each. This is exactly what we did here, right? It's exactly the same thing. 1/2 of the sets have this property for a given edge E. So this probability is just equal to 1/2 for every E. Just equal to the sum over E and E of G of 1/2, which equals E of G over 2. Okay. So this is the magic of expectation. It's easy to calculate, okay, because of this beautiful linearity property. Okay, but that's not what we wanted, right? We didn't want the expectation to be big. We wanted there to exist a set that's big. But why does it follow? Yeah, right. You can't, if for every single a, f of a is smaller than a half, then the expectation would be smaller than a half. The average, wherever the average is, some guy has to attain it. Some guy has to be at least that big, some guy has to be at least that small. Okay? This implies that there exists a such that f of a is at least e of g over 2. Okay. So notice, this proof is just exactly the same as this proof, right? Which is exactly the same thing, but we wrote it in probabilistic language. What was the point? Well, for this proof, there wasn't much point. But what we'll come to realize is that writing things in probabilistic language can be very powerful when we're in slightly more complicated situations. Okay? So this is our basic sort of fundamental example. Okay? If you want to prove something, it's often just choose it randomly, calculate the expectation, see what it tells you. Okay. If everyone's happy, let's do a second example, and this time you're going to solve it. Okay. Okay. So, let's let H be a K-uniform hypergraph. So what is a K-uniform hypergraph? So you have a vertex set, V, and your edges are sets of size K. Okay? So a graph is a two-uniform hypergraph. Okay. And let's consider, so say H is two colorable if there exists a red-blue coloring of the vertex set V of H such that every edge, no edge is monochromatic. So I'm going to write MC for monochromatic quite a lot, so might as well start now. Okay, does it make sense? So when is a graph bipartite? Sorry, when is a graph two-colorable, sorry? I gave it away. A graph is two-colorable if and only if it's bipartite, right? You can partition the vertices such all the edges are between. Okay, so question. What is the minimum number of edges of H such that H is not two-colorable? Okay, let's just, as a warm-up, let's do it for k equals 2. What's the answer for k equals 2? Yeah. Because? Shout.
Triangle.
Thank you. Right. 3. Take a triangle. Okay. So, theorem, if E of H is less than 2 to the k minus 1, then H is two-colorable. How are you going to prove it? Okay, so what are we trying to do? We're trying to show you've given this k uniform hypergraph with like 2 to the k edges. I claim that there does exist a partition into 2 parts, a coloring into red and blue, such that no edge is monochromatic. No edge is completely red, and no edge is completely blue. Okay, prove it. Great idea. So color randomly. Right. Let's say probability that V is red equals probability V is blue equals a half for all V and all independently. Right? Which is the same as saying every coloring is equally likely. Right? Okay. And now what? Well, okay, so our idea was to calculate the expectation of some random variable. So we should define a random variable. Okay. What do we care about? We care about whether or not there's a monochromatic edge. So here's the idea. Let's count monochromatic edges. We always want to count something. So let's say x is the number of monochromatic edges of H. Right? Here you go. That's a random variable. You've got a random coloring. That's a number that depends on the coloring. Okay, that's all a random variable is. You're given something random, it outputs a number. Okay, so we can calculate the expectation. Okay, so what is the expectation? Okay, it's the average. We don't care. The point is it's linear. Right? The point is the expectation of x plus y is the expectation of x plus expectation of y. Right? This is the property we're using. This property we use here, but we're always going to use. So if x is the number of monochromatic edges, the expectation is just the sum over edges of the probability that E is monochromatic. Right? Okay, what is the probability that E is monochromatic? So now we have a K uniform hypergraph. So here is E. It has K vertices. Okay, and we're going to color them randomly. I can't see, oh, there's some red. And here's some blue. Good. Okay, first one, I color randomly red. Second one, if it's going to be monochromatic, that had better be red as well. That's red with probability 1/2. Next one, 1/2. Next one, 1/2, 1/2, 1/2. If any of them fail, then it's not monochromatic, we're happy. So what is the probability they're all the same color?
1 over 2 to the k.
Yes, almost. Yeah, right. So the first one, it didn't matter. So 2 over 2 to the k. Exactly. This is always 2 to the minus k plus 1. Right? First one doesn't matter. All the others, probability 1/2 of being the same. That's true for every edge But look, we assumed E of h was less than 2 to the k minus 1, so this number is strictly less than 1. Is it okay? Okay. Why are we happy? Why are we happy? Why is this good? Right. X is counting something. So it's a non-negative integer. It's 0, 1, 2, 3. Right? If it's never 0, then it's always at least 1. In which case the average is at least 1. But the average is less than 1. So it must at least one time be 0. It must be possible that x is 0. What does this imply? If the expectation is less than 1, this implies that the probability that x is 0 is positive. Right? It can't never be 0. Otherwise, the average would be at least 1. But what does this mean? The probability x is 0 is positive in a random coloring. There must be some coloring for which x is 0. But that's exactly what we're trying to find. Right? X equals 0 implies, oops, sorry, yeah. No edge is monochromatic. Right? In fact, if and only if. That's what x equals 0 means. So we're done. So we took this crazy complicated hypergraph we knew nothing about, and we didn't construct a good coloring, but we show one exists. Just by coloring randomly and counting the expected number of good colorings. In fact, the expected number of monochromatic edges. Right? Not the expected number of good colorings. Okay. Is it okay? Good. Let's keep going. Another thing that Alex talked about in his course was tournaments. So just in case people don't know what a tournament is, it's a set of vertices, and between each, like football teams or whatever, between each two, you draw an arrow between the one that wins and the one that loses. So everyone plays everyone. Right. And you draw an arrow between each pair of vertices. Okay. What is a Hamilton path in a tournament? Is a directed path of length, a directed path with n vertices. Okay. So, how many Hamilton paths are there in a tournament? Okay, in general it's going to be hard to answer. Okay, how big or how small can we make the number of tournaments? The number of Hamilton paths? What's the minimum you can make it? What's the smallest you can make this number? How do you make 0? It's not super obvious how to make 0, I think. Sorry? Yeah. So in a transitive tournament, which means everyone goes from left to right, there's 1. Okay, so maybe there's 0. We haven't proved if there's 1 or 0, but it's pretty small. So most 1. So maybe exercise, decide if it's 0 or 1. Okay, so that wasn't such a great question, perhaps. What about the maximum? Okay, so this is not so good. Well, it's certainly a most n factorial, right? Which is just the number of all ways of doing it, all ways of ordering the vertices. So here's a theorem. I'll put it here instead. It's at least n factorial times 2 to the minus n. So it's not that much smaller than n factorial. So what am I saying? I'm saying there exists a tournament on n vertices with n factorial times 2 to the minus n Hamilton paths, at least. What's the proof? I think at this point you should be shouting it out. Sorry, yeah. N vertex. Thank you. Yeah, let's just take a random tournament. So, okay. I'm hoping as we go, you'll feel more comfortable. We're doing like the same thing every time. I don't want to do it for you. Shout out. Tell me what to do. So every time we do something random, we define a probability distribution. We then define a random variable that counts the thing we care about. And we calculate its expectation. So what is the random variable we want to use in this case? Yeah, exactly. Just the number of Hamilton paths. We call this T. Great. And we calculate expectation. Should I talk more about like the basics of expectation before we continue? Who would like to hear 10 minutes on the basics of expectation? Nobody. Okay, good. Okay, so how do you calculate expectation? Yeah, over all Hamilton paths in the complete graph, say, yeah?
If the edges are in the different directions of the following vertices.
Exactly. Right, the probability that this really is a Hamilton path. Maybe I'll call it over Pn in Kn, probability Pn is a Hamilton path in T. That's a better way to write it. Right? Okay, so given a path on n vertices in the complete graph, so an ordering of the vertices, what is the probability that it's a Hamilton path in T, that it's directed from left to right? Yeah, exactly. This random tournament, we're just picking probability an edge goes this way equals probability an edge goes the other way equals a half, all independently. Right? So for each edge, we just flip a coin. All of them have to go to the right. There's n minus 1 edges, each probability a half, independent, so just multiply the probabilities. It's exactly 2 to the minus n plus 1. For every path, it's the same probability, 2 to the minus n plus 1. Right? N minus 1 edges all have to go left to right. And how many paths are there? I guess they're directed paths. How many ways are there to order the vertices 1 to n? N factorial. Right? And why are we now done? Even with a plus 1 here. Why are we done? Shout it out so that I know you're understanding. Right. If the expectation is this, then it must be possible for x to be this big. Right? If every tournament had fewer than this many Hamilton paths, the average number could not be this big. You always attain the average. You're always at least the average sometimes. You're always at most the average sometimes. Okay? So it implies probability that x is at least n factorial over 2 to the n minus 1 is positive. That means there exists a tournament with that many Hamilton paths. Great. Yeah, please. How so? Oh, going that way and going that way?
If we pick a permutation,
Yeah.
we are counting left or right.
Right. So absolutely.
If the reverse permutation, then counts again.
Yeah, so we're counting both directions. Yeah, so we're counting the path. Yeah, I guess we're counting each path with a fixed start vertex. Because then everyone has to go to the right from that start vertex. If we start from the other one, it would be, the same path in the complete graph, but there's a different way it can be a Hamilton path in the tournament. Right? So yeah, there's two ways of looking at the path, and they can go into two different directions. So you can go from here to here or here to here. Make sense? Yeah. Yeah, thank you. So another problem about tournaments. So here's the problem. Show for all k, for each k, so let k be just some integer, anything. Show that there exists a tournament with the following property. I'll come over here for it. Tournament T for every subset of the vertices of size k there exists a vertex that beats everyone in S. So you have this tournament. You have 1,000 football teams playing. You're going to pick out the best 10. And the problem is, any 10 you pick, there was some team that beat all of them. How are we going to prove this? Does it make sense? So there exists a tournament such that any set of K teams all got beaten by some other team. There's no best K teams. What's the proof? Sorry? No. So we should not take the transitive tournament, because if we take the transitive tournament, then these K guys at the beginning beat everyone else. So no one beats all of them. So that would be a bad choice. Yeah, we want to take something sort of very far away from the transitive tournament. Very different, yeah. What's the proof? Yeah, right? I mean, I left it on the board, right? Take a random tournament, chosen in the same way, define some random variable, calculate expectation. What random variable do we want this time? What? Right, so yeah, X should encode the thing we care about. We care about whether or not there exists a set which fails to have this property. So we should count the sets that fail to have that property. X is the number of sets, of K sets, S, such that, we go to this, there does not exist V that arrows the whole of S. Okay? I hope you're okay with this shorthand. Right? There doesn't exist a vertex V that beats everyone in S. And what do we care about? So what do we want? There exists a tournament such that X equals 0. Right? If X equals 0, there is no set with this property, which is what we want. It's okay? Okay. So, again, it's some crazy random variable. Let's calculate expectation. X is the number of somethings with some property. So the expectation is the sum of over those things. The probability has the property. Okay? Or you're just doing the same thing. Sum over K sets S of probability that there does not exist a V that beats everyone. Okay, what is this probability? It's not quite so simple. Okay, so first, what is the probability for a given set V, a vertex V, and a given set S, that V arrows S? That V beats everyone in S. Equals what? Exactly, 2 to the minus k, right? There are k edges. They all have to go from V to S. Okay, so the probability that V does not arrow S is 1 minus 2 to the minus k, right? This doesn't happen. And we want that to be true for every vertex outside S. And for every vertex outside S, the edges between V and S, they're all disjoint, right? They're all different. Right? You take two vertices, U and V, outside S. These edges and these edges are different, right? So that means these two events are independent. In fact, for every vertex outside, the events are independent. So the probability that this happens for every vertex outside is what? Exactly. It's 1 minus 2 to the minus k to the power n minus k. Right? And how many k sets are there? There are n choose k of them. Okay. Now, this is looking a little bit scarier than things we were looking at before. What do we want about this number? We want it to be less than 1. So, is this number less than 1? Without doing any calculation, just by looking at it. Well, I guess it depends on what n and k are, right? K is given to us in the question. K is a constant. But what is n? We choose it. We can take it as big as we like. And what happens to this function as n gets big? Well, what is n choose k? It's at most n to the k, right? It's a polynomial. Right? This is at most some polynomial. What is this thing? This is a number less than 1, a constant, to the power n. This is an exponential. And, right, without calculating at all, we know exponentials beat polynomials, right? So obviously, when n is large enough, this thing beats this thing, and you get something less than 1, right? Without any calculation. So we're done. Right? Just take n large enough so this last inequality is true. The expectation is strictly less than 1, so with positive probability, it's 0. And that's all we wanted. Great. What's my eraser? Oh, no, there it is. Okay. Okay, let's do one more relatively simple example. And then maybe do something that's a little bit different. So, let's define the Ramsey numbers How many people have already seen the Ramsey numbers? Okay, so maybe you'll know this already, but that's fine. Equal to what? Ramsey number Rk is the minimum n such that for every coloring of the edge set of the complete graph with n vertices with two colors, there exists a monochromatic copy of kk, meaning a monochromatic clique on k vertices. Okay, so first, why does this number exist? Why is it finite? Why, if n is large enough, in any coloring can you find a monochromatic clique on k vertices? Say louder?
You can always build one if your n is large enough. Like you can get the click and then add the vertices of other color.
I'm not completely sure if I understood. But anyway, okay, let's prove it. Okay, so here's the proof. We're going to start out with a set x. Now, sorry, x is going to be a set rather than a random variable. At the beginning, it has all the vertices. Okay? And we're given some coloring, some horrible coloring by our enemy. And we're going to find this monochromatic clique. And how are we going to do it? Well, we're not just going to build a red clique. We're going to build a red clique, and we're going to build a blue clique. And as we build these cliques, we're going to shrink x. We're going to shrink x to be the vertices that only send red to this red clique A, and only send blue to this blue clique B. Okay, so how are we building these cliques? I'm going to show you one step of the algorithm, and then you see how it works. So what is the one step? One step is we pick any vertex, little x, inside x, and we partition the rest of the world according to whether it's x sends red or blue to that vertex. Okay? Pick a vertex, look at its red neighborhood, its blue neighborhood. Then just pick the larger one. Here the larger one is red. And put x into A. And replace x by the red neighborhood of little x. Okay? Then we maintain this property that A is still a red clique. The new x, x prime, is the common red neighborhood of A and the blue neighborhood of B. And we just shrunk our set a bit. How much did we shrink our set by? How much smaller is x prime than x in the worst case? Shout, I can't hear. Half. Right, exactly. We took the bigger of the two, so we lost a factor of 2 in each step. And how many steps do we have to do? How many steps do we have to do to make sure we find a monochromatic clique of size k? 2 times k, right? Right? It might be that half of the steps are red and half steps are blue, so we might have to do 2k steps before we guarantee one of them is size k. That means that if n is at least 2 to the power 2k, then there exists a monochromatic copy of kk. Right? So this Ramsey number is at most 4 to the k. Great. Okay. What about lower bound? For a lower bound, you give me a coloring that has no monochromatic clique of size k. Let me prove that it's at least k squared. Here's my coloring. If I take k minus 1 sets of size k minus 1 and color red inside and blue between, there's no red clique of size k because it doesn't fit in any of the parts. There's no blue clique of size k because you can only take one vertex from each part. Okay. So this actually proves strictly greater. Okay, so our lower bound is k squared, our upper bound is 4 to the k. Can we think of a better construction than this? So it's actually pretty tough to come up with a construction that beats this. But it wasn't, I don't think it was proved, a construction wasn't found that gave k cubed until, I don't know, for sort of several decades after this, and used some very clever linear algebra. Nevertheless, we are going to prove right now r of k is at least square root 2 to the k. This was proved by Erdős in 1947. Okay, so by now you know how to do this. Tell me what to do. Exactly. Proof, color randomly. Again, probability red, probability blue. Blue equals a half, all independently. 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 Okay, we've colored randomly. Okay, why is this good? The same thing every time. We're going to define a random variable. Thank you, excellent. Number of monochromatic copies of kk. And then calculate expectation. What is the expectation? That's right. I'll call it S or something.
You're checking if all the n is inside.
Exactly. Great. So what is the probability that a particular k-clique is monochromatic? Louder. 2 to the minus k. K choose 2, right? Every edge has to be the same color. But plus 1, because they can be red or blue. And how many do we have? N choose k. Okay. Okay, but now it looks a bit scarier. Right. So what can we do here? Well, is it enough to win? So how do we bound this from above? Do I want to do this? Yeah, I think it's fine. So I'm just going to bound n choose k from above by n to the power k. Okay? You can do better, but let's not bother. And then there's a factor of k here as well. So I'm going to pull that out. I'm going to pull this 2 out the front and say it's n times 2 to the minus k minus 1 over 2 to the k. Does it make sense? So there's an n to the k, bounding this n choose k. And then there's this 2, this one. And then 2 to the minus k choose 2 is 2 to the minus k minus 1 over 2 to the k. Right? So everything's there. Now, if I pick n smaller than, so I need to make it slightly smaller. If I make this thing less than a half, then I can make this smaller than 1. Right? I can make it smaller than 2 to the 1 minus k or something. If this thing here is less than a half, then we get the half to the power k. Right? So just make n a little bit smaller than root 2 to the k, and this is true, and this is less than 1. Is it okay? Expectation is less than 1, so with positive probability it's 0, so there exists a coloring with no monochromatic KK. Okay. So we've done 5 fairly similar examples so far, which I hope has given you an idea of how you might think about approaching these problems. Okay. So in the last 15 minutes, maybe I'll quickly do two just to show you that things are not always quite so simple, 2 slightly different proofs. And then tomorrow we'll do some proofs that need extra ideas. We're not just doing the same thing. Okay. But is everyone's happy with the basic method? Okay. We've seen it lots of times now. Okay. Here are some fun ones. So, theorem, which is again Erdős. Every set A, 1 up to n, contains a sum-free set of size at least A over 3. What is a sum-free set? There does not exist a solution to x plus y equals z. How are you going to deal with this? This is suddenly much less obvious. So what you might think is, I could take just all the odd numbers in A, and odd plus odd is even, so that's sum-free. So they're good. Okay, but what if you don't have very many odd numbers? Or you could take all the numbers that are bigger than n over 2. That's also sum free. But maybe there aren't very many of those either. So here's the idea. So we're going to think of A as a subset, not of 1 up to n, but of the cyclic group Zn. Okay, so it's going to count mod n instead of in the integers, right? This makes life worse for us because there's more sums to avoid. Okay, that seems like a bad idea, but okay. And let's assume that n is prime just by taking it a little bit bigger if we need to, right? Let's take, don't do 1 up to n, 1 up to, some slightly larger prime. Okay. And now here's the idea. Let's multiply by a random element of Zn. So here's Zn. Here's 0. I would like to find a sum-free set inside Zn that's quite big. So n is prime, so I can't just take the odds. And it's cyclic, so I can't take the second half. Doesn't mean anything. What's a large sum-free set in the cyclic group? The middle third is a large sum-free set. Because any guy here, add it to itself, you fall out. Okay, maybe open. Right? If you're bigger than n over 3, then add to yourself, any two numbers added here end up out here. And then if any two numbers smaller than 2 over 3, don't wrap round to get to n over 3. So this set is sum-free. Can you now guess what to do?
Don't you also have to add the 2n over 3 with the n over 3? Don't you also have to add the large ones with the small ones?
You do, but 2n over 3 plus n over 3 ends up here. So it's also fine. Yeah, so it's saying that what is the sum? If you add this set to itself, you get exactly the complement. So, can you see how to finish the proof? What's the idea? What is a large sum-free subset of A? Such the what? What do we call this thing? P. Take all the elements of A, but when you multiply them by this random number, this random lambda, they land in the middle third. So I want two things. First, I'd like to show this set is sum-free. Why is this set sum-free? if A plus B equals C, sum A, B, C in B, then lambda A plus lambda B equals lambda C. But lambda A and lambda B and lambda C are all in the middle third, and we just said that didn't happen unless they're all the same, but they're not all the same because we're in Zn and n is prime. Right? They didn't suddenly become the same by multiplying by lambda. So B is sum free. Is it okay? There's no sum because if A plus B equals C with them not all the same, oh sorry, not all the same, with none of them 0, it can be 0. Sorry, it's fine. Yeah, anyway. We're talking nonsense. We're talking nonsense. Anyway, it's fine, right? Is it okay? Everyone's happy? Right? Okay, so B is sum free. But how large is B? Well, it's random. But we can calculate the expectation. What is the expected size of B? Well, it's the sum over all A and A of the probability that lambda A is in P. What is the probability that lambda A is in P if lambda is a random element of Zn? So P is this entire interval. Yeah, not that it's equal to a single value, that it's in this giant interval. Yeah, 1/3, right? Right? This multiplying by lambda just permutes the elements of Zn, because n is prime. So exactly 1/3 of the lambdas take A into P. So this equals A over 3. If the expectation is A over 3, there must exist a choice of lambda when it's at least A over 3. Okay, I was going to do one more example, but instead maybe I'll just tell you a little bit about. So this is a very famous problem to determine the best possible answer here. So there was a famous paper of Eberhard, Green, and Manners, who showed that there exists a set A such that you cannot do better than the 1/3 plus epsilon times A. So 1/3 is really the best constant. Yep?
That was exactly what I was going to ask, because if you have a better choice of P, for instance,
Yeah, right.
automatically you get a...
Yeah, so sorry, in Zn for n prime, this is really this is the best thing. It depends on the what is mod 3 or something. So in Z5 you can do better by taking, you can do 2/5 or something. So this is an extremely clever construction by some very extremely famous people. Ben Green is very famous. Until recently, the best lower bound was by Jean Bourgain, who improved this A over 3 by this tiny, tiny, tiny amount. So I think this argument, if you do it carefully, gives A plus 1 over 3. And with some extremely clever Fourier analytic argument, he improved this by this tiny amount. And then extremely recently, like a few weeks ago, the student at Oxford who, someone remind me of his name? No one knows. Okay, I need to find his name. Basically, so showed that this thing is at least, I'm not sure exactly what he proved, like something tending to infinity. I need to find out his name. So this was a major breakthrough on this problem. I can find out, I think. Maybe I can't find out. No, I can't find out. Bedert. Found it. So this very simple example, in fact, it's not the only thing I've showed you today. It's a very simple example that turns out to be a very famous problem. Actually leads to very quickly to some extremely interesting and high-powered mathematics. Right. So there will be. I sent some examples. Actually, quite a lot of examples, like 30 or something. That you should have received them all. The first 15 or 20 should be sort of relatively approachable. The later ones are more difficult. If you're struggling with the basic ideas, then please don't look at them until much later. Tomorrow we'll see a bunch more examples using some slightly more complicated techniques, and then building up to the last two classes where we'll see things that are a little bit more complicated. Nothing too crazy. Okay. Great. And yeah, there should be an example class during Alex's course tomorrow, which hopefully will have some TA showing up too, unless they're all in Alex's class. We'll see what happens.